Welcome everyone to our ITMP seminar. And today we are happy to have Konstantin Zarembo, who will speak about large localization and quiver CFTs. So please start.
Yeah, thank you very much. It's a pity I cannot give this talk in person. I will talk about some work on localization in the large N limit. And the motivation for that was to understand holography in quantitative setting where one can really do calculation on both sides. So usually holography, well, I will be talking about holography for conformal theories, so it is CFT. In the simplest setting, it postulates the equivalence of a CFT on the boundary of anti-de Sitter space to gravity in the bulk. In principle, there are three assumptions that go into this statement. So first of all, the CFT has to have large central charge because central charge controls the Planck scale. And if you want the Planck scale to be large, so Planck must be large in appropriate units, then the central charge has to be large. So if central charge is infinite class, then there will be no quantum gravity effects. The other requirement is that the CFT should be at strong coupling, where the coupling controls the radius of anti-de Sitter space, again in some appropriate units. The space will be big if the coupling is strong. And the third condition, which is not so often emphasized, is that anomaly should match. Now I'm talking about four-dimensional conformal theories. If we want gravitational description to be in terms of simple Einstein gravity, then the anomaly coefficients A and C should be equal. Or actually, it's probably better to put it vice versa, that if you have Einstein gravity description in the bulk, then automatically the coefficients will be equal because they are universal and depends only on the gravitational sector of the theory. So from all this condition, it means that we need a very special CFT for the holography to work in this simple way. It has to have at least two adjustable parameters, the central charge and the coupling. And usually it's not easy to find such conformal theories. Typically, a fixed point is an isolate point in the parameter space. But supersymmetry is one way to help. And so I'll be considering theories with two supersymmetries. So in that case, the condition that the theory is conformal is very simple. It means that the one loop beta function should be equal to 0 because in n equals 2, the beta function is one loop exact. So if it's 0 at one loop, it's 0 to all orders. So one loop beta function is proportional to the Casimir of representation compared to, so it's, how should I say, it's equal to 0 when the Casimir of matter representation equals the adjoint Casimir, which is the gauge field contribution. So there are basically two ways to cancel. If you have a theory with a single gauge group, there are basically two ways to cancel the beta function. Either we take matter in the fundamental representation, and then we need the number of flavors equal to the number of colors. So this theory will be conformal, and oftentimes it's called super QCD. Or we can consider matter in the adjoint representation. Then again, the beta function will be 0, and this is the celebrated example of n equal 4 superegg so there's an extra supersymmetry in that case. And both this type of theories are conformal. So the central charge is proportional to n squared. And they have an adjustable coupling, which is just the 't Hooft coupling or the Young-Mills coupling in both cases. So when the central charge is large, then this means that the number of colors must be large. So we'll be considering the 't Hooft or the Veneziana limit of superegg-Mills or super QCD. Whereas the condition that the coupling is strong is less easy to realize in field theory, because this means that we need to go into the non-perturbative regime where the coupling is large. So if you look at the third condition, namely that the anomalous coefficients should be equal, then this condition is satisfied for super QCD. Indeed, A is equal to C in superegg-Mills. And this theory has a nice weakly coupled holographic description. The basic example of it is CFT, which is the weakly coupled limit of string theory on ADS5 cross S5. Whereas super QCD doesn't, for the super QCD, the anomaly coefficients don't match. And this means that this theory doesn't have a simple holographic dual. It may exist, but it will never be weakly coupled.
A question?
Yes.
So this about A not equal C looks like when you say not weakly coupled, it's still string coupling is still small. Lambda controls, so it's not clear that lambda controls string tension, or what is the weakly coupled? You mean Newton's constant?
Yes, of course, it's the parameter that controls of course, making n large means that quantum gravity effects are not important, but string theory will not be classical, so it will not be described by simple Einstein gravity.
Yeah, it looks like it's more like we don't have effective field theory description rather than
exactly.
Yeah.
So string theory description may exist, but it will not be string theory with a simple classical limit. So all this is visible in observable, so one can compute a Wilson loop. I'll be talking mostly about Wilson loops. In superegg-Mills, the Wilson loop nicely exponentiates its strong coupling. So the strong coupling expression for the circle Wilson loop is written down here, and it has a clear string theory interpretation. So there is an exponential part, which is simply the area law in ADS5, and the prefactor can be attributed to quantum fluctuations of the world shape. So indeed, the string tension is square root of lambda over 2 pi. Lambda is the 't Hooft coupling. One can compute the area of the minimal surface bounded by the circle. When regularized, it gives minus 2 pi. And so e to the minus tension times area is simply e to the square root of lambda. So everything matches. For super QCD, the Wilson loop simply does not exponentiate. So it goes as a power of, as a third power of the coupling with some logarithmic addressing. So there is no simple holographic description. Nevertheless, So even though these theories have a very different behavior, there is a continuous interpolating theory that in one limit becomes super QCD and is equivalent to n equal 4 super Yang-Mills in the other limit. It is obtained by, and this is the quiver CFT. So it is obtained by gauging the flavor group of super QCD. So the super QCD has SUNF flavor symmetry because quarks, the matter have they have color index and the flavor index. And in super QCD, the flavor index corresponds to global symmetry. But one can introduce an extra gauge field that acts on the flavor index, and then we will have a theory with two gauge groups and two couplings, and the product gauge group SUN cross SUN. So the number of colors for conformality should match the number of flavors. So it is customary to depict this gauge theory in the form of the quiver diagram with two nodes, each of them corresponding to the gauge group, and the matter. So the matter fields are in the bifundamental representation, so they're fundamental with respect to each of the factors. So they correspond to links in this diagram, and there are two gauge couplings. So if we set one of the gauge couplings to 0, then one of the SUN becomes a free theory, it decouples, it doesn't interact with matter anymore. And we are back to super QCD. So the flavor symmetry indeed becomes global. So we have a theory with a single coupling. On the other hand, when we set the couplings to equal to one another, the theory has an extra Z2 symmetry, because then there is we can simply interchange two gauge factors. They act absolutely symmetric on the matter fields. So there is complete symmetry between flavor and color in this special point. In fact, this point corresponds to the orbifold of n equal 4 super Yang-Mills. So let me say a few words about what means orbifold in the field theory context. Suppose that we have a gauge theory with some global discrete symmetry gamma that we can also embed in the gauge theory, in the gauge group. So there are two groups, gamma and gamma prime. They are isomorphic as groups, but they act differently on the field. So gamma acts as a global symmetry, and gamma prime is the same group, but it acts on the color indices of all fields, and it is simply a subgroup of the global color transformations. So then we can consider a projection which breaks this product of global symmetry and its embedding in color to a diagonal group, which simply means that we take all the fields that are charged with respect to the diagonal group and set them to 0. So there is a beautiful theorem due to Bershadsky and Jaganson that planar diagrams in theory so obtained are the same as planar diagrams in the parent gauge theory. So they are equivalent, at least perturbatively, at least in the planar level. So non-perturbative equivalence is not guaranteed, because there, even at large n, there can be non-perturbative effects. But in the case that we will be considering in the large n limit, this is an exact statements, so that the theories are just equivalent to one another. So the orbifold of n equal 4 is built the following way. We just consider a symmetry that acts trivially on the gauge fields, but changes the sign of matter. So obviously this is a symmetry of the Lagrangian because there are no cubic terms there, and so it is invariant under these Z2 transformations, and we embed it in the gauge group also in the simplest possible way, where we simply consider SU2N gauge theory and embed Z2 diagonally. So our orbifold projection then eliminates off-diagonal components of the gauge fields because they change sign under these Z2 gauge transformations, and global Z2 acts trivially on them. Whereas for matter fields, we have to cross the diagonal components for the reason that there is a non-trivial global Z2 action. So as a result, we get a theory with two dependent gauge groups and the matter in the bifundamental representation, because this is how diagonal gauge transformations act on off-diagonal blocks of psi. And closer inspection shows that what we get is precisely the Lagrangian of the quiver theory, but with the restriction that the coupling constants for the two factors are the same, because we started with the n equal 4 superiored Mills, where there was only one coupling constant. So to conclude, the orbifold theory is equivalent to quiver when the coupling constants of the quiver are the same. So this suggests that the quiver theory has a holographic dual that descends from the ADS5 courses 5 dual of n equal 4 superior Mills. So the proposal here is the following. So in field theory, we have to treat differently matter fields and gauge fields, and correspondingly their superpartners. So in geometrically, ADS5 realizes geometrically the gauge symmetry of ADS5 is a geometric realization of the conformal symmetry. On the other hand, the sphere represents the R symmetry, which acts most naturally on the scalars of the superrank Mills, which from the n equal 2 point of view are split into two parts. So 4 of them belong to the hypermultiplets, so they're matter fields, and 2 are superpartners of the vector fields, so they belong to the vector multiplet. And accordingly, hypermultiplets transforms non-trivially under Z2, while vector multiplet undergoes trivial transformations. So in the 6-dimensional space of scalars, there are 2 distinguished directions where the symmetry doesn't act, and 4 directions which are simply flipped under the action of the symmetry. So this transcends into the geometric picture of the holographic dual, where we can picture 5-dimensional sphere as being embedded into 6-dimensional space. And likewise, when we consider the orbifold, there will be a distinguished plane of, so this should be X5 and the X6. They are geometric images of the vector multiplet. And perpendicular four directions correspond to the hypermultiplet. So Z2 naturally acts by simply flipping these four directions. And the string dual will be a vector space where we identify points under action of this Z2 symmetry. So we simply take the sphere and squash it along the equator and fold it into parts. So this is not a smooth manifold because the fold is a conical singularity. But string theory is well defined on such type of spaces, so one can indeed define what is string theory on an orbifold. So the statement here is that the gauge dual of the quiver CFT at the orbifold point is equivalent to string theory on ADS 5 cross S5. Where S5 is modeled by the action of Z2 symmetry. And moreover, this also extends to the generic quiver theory with unequal couplings. If we identify the effective coupling with the geometric, so that there is an effective coupling which is the geometric, whose inverse is the arithmetic mean of the inverse of individual couplings of the two gauge groups. And it is this effective coupling that determines the string tension of the dual string theory. But then the question is what happens to the other coupling, because we can consider, for instance, the something that's anti-symmetric in the interchange of lambda 1, lambda 2. So what is this parameter? And it's not very easy to see it in this geometric picture because, well, I mean, if we start from this string theory on the orbifold, there seems to be no geometric parameters that can deform away from the orbifold point, unless we look closer into the orbifold singularity and try to resolve it. So this is also something that was known in string theory for a long time. So if you consider an orbifold, so let's consider a simple cross section of in the vicinity of the orbifold line here. So the transverse space would be a four-dimensional plane, which we'll also can consider as a two-dimensional complex space, on which the Z2 symmetry acts by simply changing all the coordinates to their inverses. So it simply changes sign. This is just a simple parity transformation. The origin is a fixed point, and so if we consider the vector space, it will have a geometric singularity of conical type at the origin. So from the string theory point of view, one can actually consider a space. So there is a well-defined procedure of resolving the singularity, meaning that we consider a space that is not singular. This is known as a Gucci-Hansen space. It's, if you wish, as a gravitational instanton. So it's a solution of Einstein's equations, which has some nice properties. It has it's a Calabi-Yau manifold. It has complex structure and so on. And so string theory behaves very well on this space, and it is completely smooth. But the curved part of this manifold is confined to a region of a finite size, which we can take arbitrary small. So from the distance very far away from the instanton, it will look like an orbifold. In this sense, it is a resolution of the singularity. So it replaces the singular orbifold point by something smooth. Importantly, this smooth portion of the resolution contains a non-contractible two-cycle, so that there is a small sphere that becomes that collapses when we take the orbifold limit. So its typical size is of order epsilon. So when we consider theory on the resolution, then there is a natural extra coupling that we can add to the string action. So there is a sigma model term which simply measures the area of the world sheet, and the coefficient is the string tension related to the effective coupling. But then we can add a topological term that corresponds to the theta angle dual to the windings of the string around this small cycle. So string can wrap this two-dimensional sphere, and we can add a theta term that couples to wrappings. So this is the usual theta term in the sigma model. And the claim is that it is this theta parameter on the world sheet that's due to the difference between the coupling constants. So there is a formula for that. And according to the duality, the theta parameter is proportional to is some function of the ratio of two couplings, such that at the orbifold point where the theory is equivalent to n equal 4 superang Mills, the flux is equal, or the theta angle is equal to pi, not to 0 as one might expect. And in general, it changes from 0 to 2 pi, so it is naturally a periodic cyclic variable. So one can imagine that. So if you consider supergravity or classical string theory, then it's basically insensitive to this parameter because it's non-perturbative on the world sheet, right? So the string has to wrap this cycle in order to produce the dependence on the theta angle. So it might seem that we need to consider processes that are very non-perturbative from the string theory point of view. But one has to recall that this cycle vanishes in the orbifold limit. And so if you consider some string amplitude, and we'll consider Wilson loop expectation values, so one can keep in mind disk amplitude for string that is attached to a Wilson loop on the boundary of ADS. So this string may fluctuate, and these fluctuations may wrap the vanishing cycle. So in principle, this amplitude will be represented by instanton series, which will be weighted with the instanton weight with some coefficients that are presumably calculable. So since this, so for the finite resolution, all these terms are exponentially suppressed by the instanton action, which is just the area of the vanishing cycle. But in the orbifold limit, this area goes to 0, so all these terms become order 1. So all in all, on these very general grounds, we expect that the amplitude will be proportional to the exponential of the area. This is the classical contribution from the minimal surface in ADS5 times some function which is periodic function of theta, or if you wish, it's function of cosine theta. Now, this is quite unexpected from the field theory point of view, because in field theory, I remind you that the string tension is dictated by the effective coupling, which is the some average of lambda 1 and lambda 2, and theta is basically a ratio of the couplings. So what this result tells us that the dependence on this ratio should be trigonometric. And it's unclear how that may arise in field theory. So the motivation for the calculations that I'll present later would be to actually understand how it may arise in field theory. And I will be actually able to compute this function exactly, but not from string theory, rather from starting with the path integral of the superangles.
Kostya,
Yes.
may I ask you, I have two questions. So one is I missed the point. So if epsilon is finite in this formula for W, so at strong coupling, why the corrections are not suppressed? At leading order, they're suppressed. If
They are suppressed, yes, but then we need to take the limit where resolution is removed.
Yes, but so you're saying for different couplings, epsilon is 0. Is that what you're saying?
So the claim is that the gauge theory is equivalent to string theory exactly at the orbifold point. So where we take resolution to 0. So we need to collapse this resolved geometry to a point.
But that's for orbifold, which has equal couplings.
Both for orbifold and for the quiver. So the difference between them is in the theta angle. The point is that without resolution, it's very difficult to, actually it's impossible to define what the theta angle means.
So are you saying, so for the quiver, geometry is still orbifold? Is that what you're saying? So what is the geometry for the quiver?
Well, I mean, it's from reading the literature, yeah, so this is my interpretation of the literature, that this is still an orbifold, but with a flux.
Okay.
It's not equal to pi, but equal to theta.
Mm-hmm. Because like for these conifolds, you get much more involved story where there is a resolution with these fractional branes and all that. Yeah. Okay. Yes, but that was that's n equal 1, and that's a different story. Another question, naive, about A equals C, about the previous story. So you said that we have A equals C for n equal 4. We have A equals C for the orbifold theory because planar diagrams are the same, or we can just check that A is equal to C. So for the quiver, A equal to C also is true, right? Is that right?
Just a second. Must be.
So if,
Yes, there is a very subtle point here, because the conformal anomaly only it's first of all it doesn't depend on the coupling. It just measures the number of degrees of freedom. I guess this was your question, right?
Yes. Yes.
So when we take the one of the couplings to 0,
Mm-hmm.
so strictly speaking, what we get is not just super QCD, but super QCD plus a free vector multiplet.
Okay. So that's how, yeah, okay.
So the anomaly is still much, but in a strange way. So we have two decoupled theories whose compound anomaly, total anomaly is such that A is equals to C. But if you only consider super QCD, then its anomaly is not equals to C.
But then if we add this vector multiplet, which is decoupled.
Yes.
So in principle, you can say what is due to this vector multiplet. And then we know examples like large-gen free theory due to something highly non-trivial in ADS. So in principle, you can consider combined theory. So I have in mind like this vector dualities, for example. This would be free adjoint theory, but it still will give you higher spin theory in ADS.
It is quite possible that one needs to add free vector multiplet to make sense of ADS CFT in this context. I think this is the upshot. And then A equals to C, but then so what happens is that we have two theories, and one of them is not only weakly coupled, but is not coupled at all. And duality only, duality is simple when the coupling is strong, right? So we are in the opposite regime.
Okay.
So can I ask a question?
Yes.
So you said, according to this theorem, that in the planar limit, this orbifold theory is equivalent to n equals 4.
Yes.
The theory with equal couplings. So this should translate to some statement on the string side. So this would mean that the string theory on ADS5 is equivalent to so the theory where the S5 is orbifolded with theta equals pi. Did you say?
Yes, exactly.
Is this obvious?
It is obvious because orbifold string theory is the same as the theory on the space without division by the group in the untwisted sector. So there is a sector of the theory that's exactly equivalent to strings on the entire space. But then we need to add new sectors of strings that gets open because of the orbifold projection. So the same is true in the field theory side. So strictly speaking, the orbifold equivalence holds for a subset of observables which are untwisted, which are invariant under the orbifold group. So there are twisted observables and untwisted. So it parallels very much the string theory story.
Okay, thanks.
And the theorem about planar equivalence only holds for untwisted sector of diagrams.
Okay.
So, okay. So what I will be considering is the following story. So here is the parameter space of the orbifold theory. It has two couplings, and also there is another parameter is number of colors. I will take number of colors to be infinite, and consider the regime where the couplings are very large, such that the ratio is fixed. So this is the stringy regime where ADS CFT is supposed to work. And in principle, in that regime, we can also consider interpolation between super-Yang-Mills, the orbifold point, which is super-Yang-Mills, and the super QCD, simply going along this curve very far away from the origin in the parameter space, but making this ratio small. So the idea will be to do a computation directly in the gauge theory that would be valid in this regime. And this is possible thanks to localization. So not that we can compute a lot, but we can still compute certain observables, and one of them is circular Wilson loop. So let me remind you how it works in N equal 4 super-Yang-Mills. So if one inspects perturbation theory for the Wilson loop, so the leading order will be given just by a simple tree-level diagram. And for the circle, the geometry is such that the propagators here they simply combine into constants. So there is nothing to integrate. What one gets is simply a numerical coefficient that doesn't depend on anything. So it holds true actually to second order in perturbation theory, to third, and so on. And so resummation of perturbative series reduces to a combinatorial problem. So there are only numbers that arise. And these numbers are taken care of by a simple Gaussian model, whose propagator is simply this number lambda over 8. So in a sense, we replace field theory propagators by constant propagators. And instead of four-dimensional path integral, which is non-Gaussian, we need to compute zero-dimensional path integral. Well, not path integral, but simple matrix integral, which is moreover is Gaussian. So the problem simplifies enormously. And of course, it can be solved. And this is how this formula that I showed on one of the first transparencies arises. So one can resum the diagrams or simply compute the Gaussian expectation value in the matrix model. It is given by the Bessel function of the coupling constant, and then asymptotics of the Bessel function is exponential, and this gives the result which agrees with ADS CFT. So all these numbers can be reproduced by considering string theory in ADS5. Now, if you go to, it turns out that this computation can be generalized to any n equals 2 theory. This is the remarkable result by Peston, that if you consider an n equals 2 generalization of this result, it also works. So the problem remains zero-dimensional, but the matrix model becomes interacting. So instead of the Gaussian matrix model, one gets this integral to compute, and in principle, it works for any theory with n equals to supersymmetry, conformal or not. So here I only give the formula for the quiver CFT, but in principle, one can compute it for anything else. And so you see that the Boltzmann weight is still Gaussian, but the measure is not. So in the Gaussian matrix model, one can reduce a Gaussian matrix model to eigenvalues, and then one would get this van der Monde factor, which is the antisymmetrized product of pairs of eigenvalues squared. But here we also have an extra function, which is a complicated special function that contributes to the interaction between eigenvalues of the same type and eigenvalues on the two different nodes of the quiver. So the upshot is that we can reduce the path integral of quantum field theory to a matrix type or eigenvalue integral, which is n-fold two n-fold integral in terms of matrix eigenvalues of corresponding to two gauge groups. So then Wilson loops, and there are two types of them corresponding to two gauge groups. They can be computed simply by evaluating exponential averages in this eigenvalue model. Now, even at this point, you might ask, what about Arbefeld equivalence? we know that at the level of planar diagrams, when we take coupling constants to be equal, the planar diagrams should be the same. And localization simply resums diagrams. But yes?
Question? So Wilson loop is from the untwisted sector. Is it possible to compute something from twisted sector using localization?
Yes, it is. So actually, so this is Wilson loops of individual gauge groups. So there some will be untwisted and the difference will be twisted.
Okay, okay.
And I'll show how to compute both.
Mm-hmm.
So, so here the orbifold equivalence is not at all obvious because if you set couplings equal, the integral remains non-Gaussian. But orbifold equivalence is a statement about planar theories. So we need to take the larger limit first and then check if we get yes. So what we expect to get is the Gaussian model at equal couplings because the n=4 superdiagonals is described by the Gaussian matrix model. And so at the orbifold point, we expect to find something Gaussian, but the matrix integral itself is still interacting. So how comes that that it is equivalent to a Gaussian theory? Well, one can look at the saddle point equations for this matrix model. So in the large n limit, in the large n limit, this integral can be evaluated by the saddle point in the saddle point approximation. Then one gets some equation for the saddle point, so there will be some distinguished configuration of the eigenvalues. And as usual, we write these equations in terms of the density. So the number of eigenvalues grows. There will be some distinguished distribution of eigenvalues, and the density will satisfy a set of singular integral equations that can be derived from the original matrix integral. And these are fairly complicated integral equations. So the kernel is a transcendental function. So they certainly cannot be solved in the closed form. But here one can see that indeed, if you set couplings to be equal, then the ansatz that the densities are equal goes through the equations, because then, and moreover, this complicated kernel then cancels, and what we get are the saddle point equations of the Gaussian model. So indeed, the orbifold equivalence works, but it works in this more complicated way that we need first to take the large n limit, and then it is possible to see that the most probable configuration of eigenvalues is indeed the same as in the Gaussian model. So there was a crucial observation that was first made by Suyama and Ray, that actually the same phenomenon happens even at the couplings which are different from one another, provided that both of them are large. So we can take couplings to be much bigger than one, with their ratio fixed, and then the claim is that the solution is still the Wigner distribution of the Gaussian matrix model. Moreover, both densities have the same distribution of eigenvalues, where the width of the distribution is controlled by the same effective coupling that controls the string tension. And this is, of course, consistent with ADS CFT because the minimal surface lives in ADS5, so it is not affected by the orbifold projection. And the minimal surface will be the same for independently of what happens at the orbifold singularity. So the Wilson loops will still, we expect that them to have the same exponential asymptotics with the effective couplings in the exponent. And this comes out of the saddle point solution of the matrix model. So indeed, the two couplings are equal. How much time do I have?
Sorry, so you have like about 7 minutes and maybe a bit more because we usually have like plus 15 minutes for questions.
Okay, I'll try to accelerate. So anyway, so the leading strong coupling solution was known due to Suyama and Ray, and it is simple Gaussian answer with the effective couplings. It also works very well numerically. You see that this is the solution for two couplings that differ by a factor of 2, but their densities are almost the same except for some small region near the edge of the distribution. This in particular means that at this order there is no dependence on the difference. So there is no theta dependence, which again is consistent with string theory because it's the prefactor that we expect to be theta dependent. So what we want to do is to compute this prefactor, and then we need to go one order beyond the leading strong coupling approximation. So let me show how this can be done, and maybe I will skip some of the details. So what one can do is find some smart ansatz that goes through the equations almost by default. And so one can, after carefully looking at how equations look, one can see that it is this expansion in inverse powers of the square root that is consistent with the equations. So each extra term, so first of all, this expansion is indeed the equivalent expansion in 1 over square root of lambda. That's the parameter of, this is the h bar of the sigma model. So this is consistent again with string theory. And then if one truncates it, so if one truncates it at the third order, then one has 7 parameters, which is positions of the endpoints of the cuts, 2 parameters, an overall constant, and another parameter, and then 4 parameters, which are coefficients in front of the subleading terms. So 2 of them are fixed by normalization. So it's possible to express, for instance, the coefficient of the second term in terms of the overall normalization and the endpoints. And the saddle point equations, it turns out that they close on the 3 terms. So one gets 2 relations between C and mu and A. And at the end, this leaves 3 unknowns, which looks a bit alarming because the equations this type of singular integral equations, they have a unique solution. Whereas what we find is a three-parametric ansatz that goes through the equation. So it seems that we lack some conditions that simply, I mean, there should be some extra conditions that fix the solution completely. So these conditions actually arise because this ansatz is not uniformly correct. So you can see that it breaks the boundary conditions. So the boundary, the density should go to 0 as a square root, but these two terms blow up. And since they blow up, they become bigger than the leading term. But the leading term is supposed to be uniformly larger than corrections, right? So at the boundary, this ansatz doesn't work anymore, and the series have to be resummed and matched to the bulk solution. So in other words, we'll need to separately solve the equations near the boundary. So there will be it's convenient to introduce a different parameterization for the endpoints in terms of the gap between the two endpoints, and then parameter alpha, which is an overall shift compared to the leading order. And the densities will be some scaling functions of order 1, about which we potentially know only their asymptotics at small distances. So this is the boundary behavior, and large distance behavior is fixed by matching to the solution in the bulk. So the saddle point equations then entail integral equations for these scaling functions, and what happens is that one can forget about the other endpoints. So one can the problem becomes local in the sense that all integrals can be extended to infinity. So the initial integral equation was formulated on a finite interval, but once we go into the scaling limit, the interval becomes semi-infinite, and this really simplifies the problem and allows one to solve it analytically. But still, the kernel, I mean, these are two sets of coupled integral equations with complicated kernels. And I'm not writing down the source term, but it is known function, but complicated one. So how to solve these equations? Well, let's look at the case where the interval is not bounded at all, and we have just a convolution type integral equation. Then we can simply solve it by Fourier transform. So convolution becomes product in the Fourier space, and then we can just this makes the equation algebraic and allows one to solve it. So for an equation on a semi-infinite interval, Fourier transform also allows to solve it in quadratures by the method that was devised by Wiener and Hopf. So if one Fourier transforms this equation as it stands, then one gets an extra unknown function, because the equation only holds for positive on the positive semi-axis. So on the negative semi-axis, there is a disbalance between these two terms, which we cannot constrain. I mean, it can be an arbitrary function. So it seems that when we Fourier transform, we get two unknown functions. We have one equation for two unknown functions, f and x. But these functions have different analytics, and that's the key point. So the analytic considerations here arise from the same for the same reason as relationship between analyticity and causality in anywhere, and so it's a simple so there is a simple but important statement that if you have a function that is real analytic and it's defined on the positive semi-axis and is zero on the negative semi-axis, then its Fourier transform is such that it can be analytically continued without singularities into the upper half plane of the frequency. That's mathematical statement. So projection on the space of functions that have only singularities in the lower half plane or only the upper half plane is an integral operator that so this is a simple projection operator that picks it makes out of a function and half plane analytic that picks a half plane analytic part of any function. So the solution, the Wiener-Hopf solution, exploits this property and the fact that f is upper half plane analytic and this new unknown function, which is non-zero only on the negative semi-axis in the position space, therefore is lower half plane analytic. So suppose that we manage to factorize the kernel as a product of two pieces, one of which is upper half plane analytic, the one is the lower half plane analytic. Then we can multiply both sides of this equation by G minus, and then we get this equation. And you see that this part is upper half plane analytic because it's product of two half plane analytic functions. And this part is lower half plane analytic. So if you take a plus projection of this equation, this term goes away and we can express f entirely in terms of the known source function, factors of the kernel, and the projection operator. So this is the solution of the Wiener-Hopf problem. So if R was a scalar function, then its factorization again using the projectors and taking so one would have been able to take the logarithm of this equation and do a projection. So the factorization problem is solved in quadratures by the same projection operators. But for matrices, there is no plug-in formula for matrix factorization. So analytic matrix factorization is known as the Riemann-Hilbert problem. And it is very useful it arises in many places, in particular in integrable systems and in algebraic geometry and just in quantum mechanics. And so for a matrix that has random entries, there is no way to solve this. There is no known formula that would produce a factorization for any matrix. But surprisingly, for the kernel that arises from the saddle point equations in N=2 quiver theory, this Riemann-Hilbert problem was solved, and actually this happened relatively recently. There is a very beautiful mathematical paper by Antipov, who solved this equation by brute force using some properties of hypergeometric functions. So let me present his solution in the language that I find more understandable for a physicist. So suppose that we consider a Schrödinger equation with some potential of this shape, and we want to consider the scattering of transition and reflection amplitudes of this potential. Then the scattering problem can be formulated in terms of the Yost function. So we can consider functions that have simple asymptotics at plus and minus infinity. So there is an infalling wave from the left, outgoing wave from the left, the same from the right. So there are in total 4 Yost functions, but there are only 2 solutions to the Schrödinger equation. So we can choose any 2 functions as the basis and relate the other 2 functions through them with some coefficients that depend on the spectral parameter, which is the energy. So this matrix that relates them is just the S matrix of this quantum mechanical problem. Well, one can just write this definition of this matrix as the relationship between Wronskian matrices built on the Yost functions. But one of the fundamental properties of the Yost functions is that they are analytic, they are half-plane analytic in the momentum. And so this formula is an example of analytic factorization. If you know the S matrix, and if you are able to reconstruct the potential that leads to this S matrix, then you can solve the factorization problem. So factorization problem, in a sense, is the not in a sense, but it is strictly equivalent to inverse scattering problem in quantum mechanics. How to reconstruct partial waves knowing this matrix. But in this particular case that we are interested in, fortunately, there is a potential which reproduces this matrix as an S matrix, and then the Yost functions can be computed in terms of the hypergeometric form. And so the Wronskians made out of these hypergeometric functions do factorize the matrix that we want to factorize. So skipping many details, one can write down the answer for the scaling functions. And then one can recover the remaining 3 conditions that were missing from the bulk solution. So one of them guarantees that these functions have the correct square root asymptotics at 0, and the other 2 conditions are matching to the bulk. So from that, one can completely fix all the parameters. In particular, one can compute the position of endpoints of the distribution. So this here they are plotted as a function of the theta parameter. And one can compute Wilson loops. So here I write the answers for the twisted and untwisted Wilson operators. And quite remarkably, they are, for the most part, they are trigonometric functions of theta. So theta, I remind you, is just the ratio of the couplings. But so when we grind through all of this Wiener-Hopf machinery, what we find is that these are nice and very simple trigonometric functions. So this is the main result. What does it teach us? Well, one thing is that the answer is actually singular. So when we take theta, so the answer is simple at theta equals to pi. Actually, it's equal to 1 for the, here I plot the untwisted Wilson loop normalized to the n equals 4 answer. And as expected, it should be equal to 1 theta equals to pi. This is the Roby-Fold equivalence. But then it blows up at the super QCD point where theta goes to 0 to pi. So it follows this intuition from string theory that something wrong should happen when one of the gauge couplings goes to 0. Unfortunately, this singularity is actually very strong. It's the dependence here is so it diverges as a cubic power of theta. And so this probably means that the instanton series that presumably are behind this calculation on the string side are not very well defined, or at least I actually don't know how to interpret it, but let me just formulate the puzzle that arises here. So if one wants to compute this function on the string theory side, what it boils down to is the partition function of the C2 over Z2 orbifold, where the world sheet is ADS2, which is just the classical solution for the circle Wilson loop. Well, and the target is the C2 over Z2 orbifold, which we have to deform into the Iguchi-Hansen solution, then introduce theta angle, then compute, and then take the size of the resolution to 0. So before resolution is removed, presumably this can be written as a series in worldsheet instantons, where the instanton action is proportional to epsilon, to the resolution parameter. And the amplitude is well, presumably it's just a number. One can try to compare this with the localization prediction by simply expanding this in the Fourier series again. But if one tries to do it, then the Fourier coefficients are all infinite because the Fourier integral simply diverges. So it's ill-defined, but possibly, well, I don't know how to regularize this integral, or maybe on the string side, the limit of epsilon going to 0 and resummation of instanton series don't commute. So let me probably finish on this puzzling point and just mention that this calculation was generalized to arbitrary quivers. One can define quivers of Zn. There's a very beautiful paper by Hao Yang who solved these equations in full generality. So there are expected divergences at theta equals 0 and 2 pi, but they seem to be too strong to define individual instanton amplitudes. But maybe these amplitudes can be resolved. So anyway, the question is about the sigma model, which has been studied quite a lot in string theory. This is the basic example of the string orbifold. And so maybe one can just, well, understand how to recover these field theory results from the worldsheet perspective. So that's all I wanted to say. Thank you very much.
Thank you too. Are there any questions?
So on string side, is there, so you think there is a unique resolution, or there should be some universality in how you resolve the singularity? Or
I'm not a specialist in orbifolds and their resolutions, but my understanding is that in this case, the resolution is unique because you want so you want the sigma model that is still conformal, and the only way to prevent it from flowing away from the orbifold is to preserve supersymmetry.
Yeah.
Preserving supersymmetry means that one needs to deform the space into something that is still a Calabi-Yau manifold, and Calabi-Yau manifolds are pretty rigid, so there is just a single one parametric way to resolve this into a Gucci-Hansen space.
by Calabi-Yau, you mean what you glue into?
Yes.
Okay.
Question? What about the superconformal indices? Kini, Minvala, Maldacen, and Raju introduced superconformal indices to test ADS CFT and show in the standard situation and show that it works. What about your situation? Can you check this duality with the help of superconformal indices?
I don't know. It's a good question. It's I simply don't know. This would be interesting to look at. This would correspond to to a different matrix model that counts.
Yeah, but it also gives a strong this rigorous checkup.
Yes, absolutely. I agree. This would be a very interesting calculation to do.
Excuse me, Kostya. If I'm not mistaken, this has been done by Gatter, Rastelli collaborators.
Yeah, it's was it I thought I read their papers quite carefully, but maybe I forgot something.
I'm not sure that it's the same quiver theory. Are you sure?
Yes, of course they did study. So what I do remember them doing is that they did study very carefully the spectrum of protected operators. So on the gauge theory side, they certainly know what the indices would be. I don't know if they compare this to string theory.
No, that's what I'm meaning.
They also did spin chains for non-protected operators, and one thing they were able to show is that this theory is not integrable away from the orbifold point.
So one thing I think they matched was the superconformal index of the twisted states in the bulk with the appropriate operators on the boundary. So at the level of KK spectrum plus string spectrum in the bulk, they pretty much matched it to the boundary single trace operators.
Yes, but did they do just matching state by state, or they did some counting using generating functions, which would be indices?
I think both are done.
Both are done.
Yeah.
Yeah, maybe. Yeah, well, thanks for the comment.
Sure. I have a couple basic questions. One is, you said the dependence should be trigonometric, but wasn't there a theta minus pi in the untwisted version?
Indeed. So it's not quite trigonometric, but of course, I mean, if you can say that any function is trigonometric in a sense, right? Because x is equal to arc cosine of cosine x. So it's a bit of a loose statement what means being trigonometric. But the twisted partition function is actually, so the question is analyticity, right? So this is not an analytic function of e to the theta, not in any sense, because it depends on this is actually, so this form actually depends on theta lying between 0 and 2 pi, right? So it's not manifestly periodic. Whereas this formula is manifestly periodic function of theta. So I don't know why there is such a difference between twisted and untwisted cases. It just came out of the calculation. And on the gauge theory side, from the very beginning, theta is not a periodic parameter.
Right. And another question, is the divergence at the QCD point expected from field theory? I thought the SQCD would have a well-defined value for its Wilson loop also.
It is, in a sense, expected because in super QCD, the Wilson loop is not exponential. So the exponential should somehow disappear. So there isn't certain non-commutativity of limits. So for instance, one cannot recover super QCD by simply setting theta to 0. So the limits of couplings going to infinity, and then taking one of them to 0 does not commute with first taking one to 0 and then taking the other to infinity. So these are different limits.
Okay, thanks.
May I ask a question?
Yes.
I have a question. In general, if you want to compute 1/n corrections to these matrix models with n equal to supersymmetry, this is very difficult because of the H function, and methods like topological recursion seem hopeless. But in this case, you have planar equivalence with a simple theory, which is n equal 4. Do you think that there could be some simplification in working out, for instance, the first correction in 1/n?
So first of all, this one thing on which I'm working right now, and I think it is possible to do it in a very related case, which is n equal to star theory. Actually, first 1/n correction was computed by Chen Lin, but I think that real simplifications occur at strong coupling. So indeed, at the orbifold point, things may become simpler, but so because orbifold equivalence only holds at the leading order in 1/n. So beyond that, all hell breaks loose. So there is no relationship between the theories beyond large n. But at strong coupling, it seems, just looking at the formulas, it seems that the analogy to Gaussian matrix model, although it's not completed at subleading orders in 1/n, still there are enough simplification that the problem may be feasible.
Oh, thank you.
Could I ask? Kostya, hello.
Hi, Carlos.
Hello. May I ask you two questions? And one probably is related to what was pointed out before. In the limit in which theta goes to 0, you come back to the case of super QCD, if I'm not wrong, making one of the lambdas equal to 0, right?
Yes.
So there is something that is qualitatively different about that theory and the theory with the two nodes gauge, that is suddenly a flavor symmetry appears. So in this sense, the quivers that you study here in your paper and the ones Ouyang studied, they are all quivers where they are all color groups, right? So they are basically circular quivers with color groups.
Yes.
Would it be possible to repeat your study in the situation in which, say, you engage two of them and you put two nodes such that still NF is 2NC all over, or any other combination of color, but also genuinely flavor groups? What would be the difficulty of that?
It's possible to do. It's actually much simpler. If you want, I can send you notes on that.
Okay, yeah, I would be very interested.
But yes, so there is also very interesting work by Uleman who solved linear quivers in D
in
equals
5D,
5.
right? In 5D.
So in 4 dimensions, it seems that quantitatively it's little different, but qualitatively it works more or less like in this case.
I see. Its second question is the following. Here you are doing the orbifolding, so in this case by Z2 or Zn in the case of Ouyang, on the S5, if I were to take ADS5 cross S5, right? So some other interesting theories is when you do the orbifolding on the ADS part, right? And that leads you basically ADS5 modded by Zn to certain 2+1 dimensional theories. And I'm wondering, the theories are very different. They still have 16 SUSIs, but they are not conformal. I'm wondering if the way you see it with the matrix model, if calculations could be exported to that case, or you think it's going to become very difficult from this viewpoint, from the viewpoint you discuss?
I don't know. Actually, this is the first time I hear about orbifolding ADS5.
Yeah, it can be done. I can send you a couple of papers where that's done, and it has a very nice. There is a very nice story there. Okay, I can send you, no problem.
Is it related to dipole type theories?
No, not in this case. Not in this case. Not in this case. No.
Then I cannot comment because I'm not familiar with this example.
No problem. Yeah, no problem. Thanks very much.
Okay, it looks that we don't have any further questions, so thank you very much. And thank you everyone for coming. Hope to see you next time.
Thank you.